In this video, we will be looking at a new concept called spanning trees. Here's our definition. A spanning tree is a connected graph. Connected graph means that you have to be able to get from one vertex to every other vertex in some way. So it's a connected graph using all vertices in which there are no circuits. So we use all vertices, right? Every dot's connected, but there's no circuits. There's no like loops. When I say a loop, right, you go from one vertex to another vertex to another vertex to another vertex to back home, right? That's kind of what we think of as a circuit, is going, starting somewhere and coming back. In other words, there is a path from any vertex to any others, but no circuits. So let me give you an example in the graph below. I could connect A with C, and I could connect C with B. And then if I somehow connect D as well, and I just did it, this is a spanning tree. Spanning tree connects every vertex, but there's no circuits. You'll notice there's no loops there. There's no way to go from A to B to D and back to A without repeating. All right, let's take a look at that same graph. Well, excuse me, the same collection of vertices, but the different possibilities. All right, so here are some different possible spanning trees for my graph above, A, B, C, D, right? We could have A here, B here, C here, D here. That can be connected in that way. Could be connected in the second fashion here. There's another connection that's a spanning tree. There's another connection that's a spanning tree. There's another connection that's a spanning tree. These are all examples of spanning trees. So you may be wondering, the question is, what is not a spanning tree? Well, that goes back to the definition, which says, as long as you have a connected graph, and as long as you don't have any circuits, then it should be a spanning tree. So I'll give you an example of one that is not a spanning tree. What if you connected it in this fashion? If you went from A to B, A to C, B to C, and then you did C to D, and then A to C. That is not a spanning tree. And it's not because you'll notice that A, B, and C has a circuit inside that, right? It's not an Euler circuit and it's not a Hamiltonian circuit, but it is a circuit in that it's a closed loop. So that's an example of what is not a spanning tree. Let's go on. Okay, this question asks, which of the graphs below are spanning trees? You might pause the video before I give the solution. Okay, well, the first one is a spanning tree because it connects every vertex and there are no circuits. This one, second one, is not. And the reason it's not is because it's not connected. It's not connected. Like, for example, if I call this bottom point A and I call this other bottom point over here B, there is no way to get from A to B because there's no edge and no pathway from there to there. All right. The third one is a spanning tree. And the last one is not, for a different reason. And the reason is there is a circuit. And you can see that circuit in that triangular portion, right? That's a closed loop. So only two of these, the first one and the third one, are actually spanning trees. Okay, spanning trees typically have edges with weights. And so let's give it a little reason why. You might look at this and go, what really is this? Well, it's a way to connect different places together. And we don't need a circuit if the connection is all we need. So one example might be like a network. Let's say I wanted to connect computers A, B, C, D, E, F, and G, and all I really need is some means of wire, right, or some means of communication. And these days, we don't always need a wire, but some sort of connection between any one of the computers. If I can get from A to C, right, then I could get from C to D, and I could get from D to G. So that means there is a pathway to get from A to G. So this is typical for a spanning tree to have edges because we would know something about the mileage needed or the time needed or the cost needed. And so that's why we put weights along the edge. All right. We do not want a random spanning tree. Okay. You don't just want to, from the, what I gave you the example at the top is all of these are examples of spanning trees. So why don't we just pick one at random? We don't want to do that. We want something called the minimum spanning tree, sometimes called the minimum cost spanning tree. We want to create a spanning tree that is as cheap as possible. So I'll give you an example of what I mean. Let's say that I had these vertices in the graph at the bottom, right? I had A, B, C, and this middle one, D, all right? And let's say I happen to know the cost to connect each of the vertices. I knew the cost, and you can see it listed on all the edges. Now, I know what I have here. This is not a spanning tree, right? This is not a spanning tree. It's actually a complete graph. I've connected every vertex with every vertex. But what I would want is I would want to make maybe possibly one of these spanning trees above in the cheapest way possible. Now, that's why we have the edges. Now, you can see the cheapest edge is 3, right? And then the next cheapest is 4, and the next cheapest is 5. Now, that doesn't always work, but it worked this time. It worked this time because if I connect those in that fashion, all of the vertices are connected. So my minimum spanning tree, or we're going to call it MST, would actually be if you just arranged the vertices in the fashion that they are and connected them with the connections that I made. Connect that to that, that to that, and that to that, right? That's the graph. And the weight of that would just be the weight of all of these edges added together. 5 plus 4 plus 3, 12. Now, if you look at the examples of above, they are spanning trees, but they're not minimum spanning trees. Let me take one, for example, this one right in the middle, all right? If you look at the edges that are highlighted and compare to the information I gave below, right? This edge has a weight of 5, essential weight of 4. Oh, and I just noticed that on my graph at the bottom, I didn't have a edge here. So let me put an edge there. Maybe this one had weight 7, so that would be a larger weight. Let's take a look at the next one to the right. What if we had that connection? Well, this would have weight 5, this would have weight 6, and this would have weight 8. And if you add that up, you can see that that's going to be 19. All right, this is a weight of 19. I didn't add the previous one up, but this would be a weight of 16. But we found a way to get the weight to only be 12. Okay, so what we want is the minimum spanning tree. Let me give you an example, maybe kind of sort of a real life example. A company requires reliable internet and phone connectivity between their 5 offices named A, B, C, D, and E for simplicity in New York. So they decide to lease dedicated lines from the phone company. They want hard lines in the ground, right? The phone company will charge for each link made. The costs in thousands of dollars per year are shown in the graph. So we want to connect these in the cheapest way possible. So what I'm going to do visually is just like kind of look around and look for the cheap edges. It looks like that one's pretty cheap at $4. This one's pretty cheap at $5. I also see this one's really cheap at $6. Oh, actually, now that I read the graph differently, that one's $9, isn't it? So let's see. This one seems to be cheap at $6 right there. But so far, I've only connected A, B, and C. And so, this brings a question to my mind. Did I really need to draw that line in that I just drew right there? In other words, when I drew my last line, did that really help me out any? Not really, because if I go back to where I was, if I erase that, I still have A, B, and C connected, right? Because this is like a wired line. So maybe I'm just still, all I'm looking to do is connect D and C to what we already have existing. So maybe the cheapest way would be to connect here and connect here. That would be a spanning tree. And I believe it's the minimum cost spanning tree because the weights would be 5 plus 4 plus 8 plus 7, which is 24. And this, if you read this problem, that would be $24,000 per year. Okay, time to practice a little bit of spanning trees. Right now that you've practiced, I hope that you learned a little bit more about what makes a spanning tree.